Thank you everyone for joining us in this virtual informal system seminar. Today we have as a guest and speaker Nathalie Ayi. She's an assistant professor at the Jacques-Louis-Lyons Laboratory at Sorbonne University, Paris. Before joining the Sorbonne University, she was a postdoctoral fellow in the Ipso INRIA team at Rennes, and she received her PhD degrees in mathematics from the University of Nice Sophia Antipolis in 2016. She's basically mainly interested among her interests, there is partial differential equations with, in particular, kinetic theory and study of scaling limits. Today, she's going to give a talk about collective dynamic models with time-varying weights, and she's going to discuss mean field and graph limits in these models. So, dear Nathalie, the floor is yours.
Thank you very much for the introduction, Renel. So, thank you for the invitation. I'm very glad to be able to present you this work. This is actually the first time I'm going to present it, so I'm happy to do it. Okay, so as Renel said, this work is about taking an interest into two kinds of continuum limits for collective dynamic systems where there is weights which are involved and which happens to evolve with time. So this is a work which has been done in collaboration with my colleague, Nathalie Ayi. So let me start with the general aspect of this model. So it belongs to the class of social dynamics models. So basically, this is the equation we will be interested in. And so xi is represent the opinion of an agent I. And this opinion can evolve because of interaction that he has with other agents. And the coefficient Aij, it's what is called the interaction coefficient, and it's actually it's a way to represent how the interaction between J impacts the evolution of the opinion of agent I. One of the classical example that I will be started with is the Exelman-Krauss dynamics, where here your interaction coefficient has this particular form, which is you take a function A, which is called the influence function, and actually Aij, it's equal to A of norm of xi minus xj. So here the interaction go through this coefficient. So this is a quite classical model now, which has been a lot studied. And for this kind of general class of models, there are several questions you can ask yourself. One of the first type is the question of what I call self-organization, and which is basically about the long time behavior. So typically for this kind of model, you notice that you have the emergence of well-organized group patterns, which naturally appends. So for instance, in that case, for the Exelman and Krauss model, you see that you can have two types of behavior. You can have your agent who reach consensus. So at the end, they all have the same opinion. And it basically, if your interaction function is compactly supported, you can see the appearance of clusters. So this has been studied a lot in the literature, but actually this is not the aspect of the problem that I will be interested in the rest of my presentation. I will be concerned about a second type of question you can ask yourself about those models, which are the large population limits. So basically, N is your number of agents, and you are wondering what happens when N goes to infinity. So there is two kind of approach that you can be doing when regarding this problem. The first one is what I will call the classical one, because this is the older one, which is the mean field limit. So in that case, you are no longer into following each agent and knowing each agent's trajectory. You are more interested into what I will call the big picture. And basically, it's enough if you know how evolve the probability density. So basically, you have a limit measure, and it represents, I'm sorry, I have a problem with my, I'm sorry, I've lost my, okay, sorry. So you have a limit measure, and at the end, this measure, it represents basically the density of agents with opinion X at time T. And that's what you're interested in. You do not care actually what kind of agent are here, how many do you, what kinds, what are their names. And in the case of the Exelman-Krauss model, it is known that the macroscopic equation that you obtain, so when you go to the mean field limit, is this non-local transport equation, which is right here, and which involves, as you see here, the interaction function. So this has been done, study, and it is now well known for this kind of model. Let me say the limitation about those kind of questions is that you have to suppose some indistinguishability of the particles. Basically, you have to be in the case where you do not care if you switch the label of the particles between them. And actually, this kind of reduces the span of models that you can study because of this, property that you must satisfy. So another way of, so that was the kind of the point of this new approach in order to be able to deal with maybe a larger span of models. And which is the second one, which is more recent and which is due to some recent development in the graph theory, and which is called the graph limit. So let me start with an example, which is what I call the L nearest neighbor interaction model. So basically, this is this equation that you can see right here. So it describes you how agent I opinion evolves. And so the thing is, you can see this equation as a system of ODE on a graph, and a graph with its vertices are 1 to n, and its edges are, in that case, ij, such that the distance between I and j is smaller than L. So basically, this is that picture that sum up how the interaction will happen, and you can interact with your neighbor at your left or at your right. So contrary to the previous model, what I didn't say about the previous model is that basically you can see that every agent can interact with every other agent. The only condition is that the distance between the two agents belong to the support of the interaction function, actually. So there is no an underlying network between behind that. And this is different from this approach where you can see that there is a network which explain how the interaction will happen. So this is one way of representing it. Another one, which is also a good way of seeing what happens, is it's thanks to that function right here, WGN, which starts from the interval O1 square. And basically, now S and S star are continuous indices. And you divide your interval into sub-intervals, and you use those sub-intervals to characterize this function in function of the edges of your graph. And so when you define this function this way, you actually have you can represent the support of this function, and this will represent your interaction, your agency matrix associated to your interaction. And as you can see, when you here, it's quite easy to see what will happen when n goes to infinity. And that's what is represented in that picture. And so this is another way of representing things. And what is interesting here is that actually that limit W, which will be a function which will be very important in the rest of the presentation, here happen in that example to be the indicator function of the interval OL of S minus S star, normal of S minus S star. So this is just an example to show you a different kind of systems where you saw now that there are networks which are behind it. But now let me be a little more general. And so before being a little more general, actually in that context, so for Exelman-House dynamics, I told you the mean field limit was the non-local transport equation I show you. Actually, for those kind of models, the graph limit, so the continuum limit which is associated to that, will be that function which is here. And as you can see, this limit function W is involved into that expression. So let me be a bit more general. So the result is due to Medvedev. And so what did he prove exactly? So he started from the interval O1. And as I said before, he divided into sub-intervals. And let's start with the function W here, which is a function from I squared to R, and which is called a graphon. So we will be interested in the following on weighted graph, where the vertices are 1 to n, the edges are 1 to n squared, and where there will be weighted associated to the interaction, and which will be defined through this graphon function that we have taken here. So basically, we are just taking the average on some sub-intervals of this graphon. This will be the weight associated to our discrete dynamics. And so what he studied in his paper is the nonlinearity equation on this weighted graph, where you can see, so now phi is your interaction function, and here is the weight that I've defined right here, and which involve this graphon. Here is a representation of the graph associated to that equation. And in the case of Medvedev, actually, he studies symmetric graph. So the interaction of 1 on 2 and 2 of 1 is the weight, sorry, is the same. And what his result is? So his result is the following. If your graphon belongs to L infinity, what it will be able to prove is that, so I will just be quick on that because I will go back on that right after, is that this function here, x subscript n, is a quantity which is associated to the discrete dynamics, but which is recasting in a framework where it can be compared with the function x which belongs to L infinity. And so this is why it makes sense to look at this convergence in this space of function. I will be more precise about how we recast the discrete system into that form. But basically, if your graphon is bounded, well, you have a convergence to x, and x happen to be a solution to this non-local diffusive equation, which I call the graph limit. So this is the result. Medvedev have been established in 2013. And that was actually the beginning of our discussion with Nastasia, because Nastasia, she studied in a previous paper a different variant of the social dynamics model that I will present you right here. So she studied this opinion dynamics model, where now, as you can see here, you have a weight which is involved. And basically, what does this weight represent? It represents the charisma, the popularity of a person. So you can see that how the interaction of J will impact agent I. It's proportional to the weight of agent J. And this weight can also evolve in time, and it's coupled with the evolution of the opinion. So now in our model, as I say, Xi is still the opinion, Mi is the weight, the charisma, the popularity. We will be in the case where we start with masses such that the sum of the mass is equal to n at time 0. Phi will be still the interaction function, and actually in all the example I will give you, we will take the same form as in the Excelman-Krauss dynamics. And we always will be in the case where the sum of psi I is equal to 0. So basically, we always be in the case where the total mass is conserved. So in our context, actually, you just will have weights which switch from an agent to another one, but the total mass is conserved. So Nastasia studied this model in some papers with the co-authors. And when we started to discuss, we were wondering, so she was more focused about the first type of question I've talked to you about, self-organization and this kind of things. And when we started to discuss, we were wondering, okay, so when we are interested in the second type of question, does it make sense in our new context to look at a graph limit? And if it does, can we rigorously obtain it? And actually the good news is yes, and this is what I'm going to show you. Okay, so the rest of my presentation is as follows. I will spend some time on the graph limit, which is the main result of the paper. Then I will be quick about the mean field limit by the classical approach, because I will spend more time on the third point, which is what was interesting for us in that paper, is that there is a relation between the graph limit and the mean field limit. Actually, there is a subordination relation. The mean field limit happen to be subordinated to the graph one. Okay, so the graph limit. So here I rewrite our model. And so as you can see now on this picture, the difference with before is that we no longer have a symmetric graph. As you can see, the weight from the interaction of 1 and 2 is not the same as the interaction of 2 to 1. And also the weights evolved in time and in a way which is coupled with the opinion. So the question is that, can we still apply the result of Medvedev in that context? Okay, so this I just already said it. Okay, so the thing is, this is something that I've been quick about before, but I have to be a little more specific about it now, is that as you can see, when you start, you have, when you are interested into your discrete system, you have vectors. You have the vector x1, x2, x1 of t, x2 of t, xn of t. And you want to compare it with the function x, which actually happen to belong to an infinity. So you have to recast it in the same framework for the comparison to make sense. And one way to do it is to use this operator that I call PC, which is just the following. You transform your vector into a piecewise constant function by doing that, just that. So it's quite clear on the picture what you do. So now you've started from vectors, which are those vectors right here, and you obtain a step function, which you will be able to compare with your solution to your graph limit. So this is one way you have to go. And actually you also have to go the other way, because I don't know if you remember, but when I presented you the result of Medvedev, the thing is, it was starting from a graphon, and the weight was defined by averaging the graphon on some sub-intervals. And so we have to do the same process, and we will start actually from continuous initial data that we will transform into vectors for our initial data for the discrete system by this averaging process, which is right here. And so this is what is represented on this picture. So we have to do that transformation in order to take our initial data. And we also have to do it for the mass dynamics. So we will start from psi, a function from I times L infinity times L infinity. And we will average it on the subinterval II for the function, the discrete mass dynamic psi I. And where here, X subscript N and M subscript N are the step function associated to the discrete dynamics that I've defined before. So it's the same process as Medvedev did, actually. He was started from a graphon and he defined his weight this way. Well, we define the way our mass dynamic or discrete mass dynamic will be taken by the same process. And so the main idea, what makes it work, is that once you have recast your equation in that new framework, you start from your discrete equation and you recast it into this step function framework. Well, you can see that, okay, let's start with initial data x0 and m0 in L infinity. Here, we will working with functions satisfying this property in order to have the sum of the mass equal to n at beginning, as I said before. Well, the thing is, if you are a solution to this discrete system, well, you are X subscript n and M subscript n happen to be solution to that continuous system, which look much more like the graph limit we are trying to reach. And so that's good news. It will be easier to compare with that. And so it works the same way. It's actually equivalent. So this is how now we have the good object to compare to our graph limit, which is basically those quantity X subscript N, M subscript M. So this is the beginning idea. You recast it this way. And so let me just say that one of the things we have to check, of course, to be able to prove the graph limit is that, well, it makes sense to look at that. So basically that there exists solution to this graph limit. And so in order to do that, we have taken the following hypothesis. Well, the interaction function satisfy phi 0 equals 0. This is just technical. It just simplifies the computation, but it can be relaxed. But actually what is important here is that phi has to be Lipschitz. And psi, which is our mass dynamics, it has to be uniformly Lipschitz with regards to M and with regards to X. And also it has to be to have a sublinear growth right here. With those conditions, we are able to prove that there exists a unique solution and this solution belongs to that space of function. So that is actually quite classical, and the proof is as follows. Well, you start by proving that the decoupled system, there exists a unique solution for that decoupled system. So basically in here, you replace M and X by M tilde and X tilde, which are decoupled. And for that, it's just fixed point theorem that you use to prove that there exists a solution. You use your Lipschitz, mainly your Lipschitz properties in order to obtain the good inequalities, and you do a fixed point theorem, and it works quite well. You have a solution for this decoupled system. And then once you have done that, you are interested into the following sequence, which is right here. And you can use the previous results to prove that there exists a unique solution to that equation. And not only there exists a unique solution, but actually you can prove that this is a Cauchy sequence. And once you have done that, you pass to the limit on that equation, and it's over. You have accomplished what you wanted to do. So this is quite classical, actually. And the fact that we have another equation, it works quite well. You just have some additional computation, but it works quite well. And so that brings me to our result, which is the following. So we suppose we have hypothesis 1 and 2 that I've shown you before. Then your solution, so associated to your discrete system X subscript n, M subscript n, are solution of this equation. And you can show that when n goes to infinity for this topology, so we will be looking at things with this norm here. Well, there exists a limit, which is called xm, and which belong to those space and function. And those limits happen to be solution to this equation. So this establishes the graph limit, actually. And so how do we do that? So the idea is the same as in Medvedev's paper. We just have additional computation again, and we have to be careful and to bound properly the good quantity in order to be able to prove the result. But the idea is the following: you are interested into psi n and zeta n, which is respectively the difference between x subscript n and x, and m subscript n and m. And so you start from the equation associated to xn, mn, and x and m. You subtract them, you integrate them, and when you do that, you obtain this inequality. And as I said, you see that those quantities here are some constants associated to the Lipschitz bound or to the bound of the quantity mn, etc. And so you are able by the same process to bound these two quantities here. And then once you have done that, you simplified by zeta n and by a norm of zeta n and by a norm of psi n, and you obtain this inequality. And you use Grunwald's lemma to obtain here this inequality. And you are able to conclude because you have taken the good initial data here, so it goes to 0. And Gn, I'm not going to go into details about what this term look like, but you also are able to prove that it converges to 0 thanks to the hypothesis, the Lipschitz hypothesis you have taken on your on the beginning. So again, it's really the same idea of Medvedev proof. We just have additional term, and we have to be a bit careful about them. But we were surprised that it worked quite well, actually. So let me give you an example in order to be a little more concrete about the kind of model that we can be interested in. So we consider a population which is divided into K groups. And in each group, you have two types of people. You have leaders and you have followers. And the thing is, we have the mass dynamics, which is right here. And what does it describe? It will describe the fact that if you are a leader, how will you, so the leader, how do you know if you're a leader or a follower in the interval? It's thanks to this quantity R, which gives you the proportion of leaders in your group. And basically, if you are a leader, you know, it's toy models. It's just to look at if things work well. If you are a leader, your weight will grow proportionally to your own mass and to the total mass of the followers. And if you are a follower, your weight will decrease proportionally to your own weight and to the weight of all the followers. And so this is the mass dynamics we tested. And so by the same process I showed you before, you can see what is the associated microscopic dynamics, which is basically the one which appears here. So it's just the discrete version of what I said before. And so some figures to show you. So we have tested two things. The first one is one group, in which one you have 10% of leaders. So in that example, you have 20 agents. So you have 2 leaders. And so which are here, so which are the blue one. And as you can see, well, actually, the weight of the 2 leaders increase very quickly to sum up to the total weight of the system. And one thing which is interesting is that you can see in that case that you reach consensus, and that the consensus that you reach is actually close to the initial position of the leaders. So basically the rest of the population, which are the followers, they are driven through this towards, the position of the leaders. Okay, and so a representation of our result, which is the graph limit aspect, it's here. So this line here, it's the opinion, the evolution of the opinion, and this line here is the evolution of the mass. And so as you can see, you see that you are going through consensus because it's flat. So as you can see here, consensus has not been reached yet, but you're not that far away. And the other thing which is interested here is that you can see that your total weight will be concentrated on 10% of the population, which are the leaders. And this is an illustration of the graph limit because on the black curve, it's a representation of the actual solution to the graph limits I have shown you. And in red, it's the function xn and mn associated to our discrete system for only 100 particular agents. And for 100 agents, it's already quite good, actually. The second illustration is that in the case in which we have 2 groups. And on the 2 groups, we still have 10% of leaders. So if we have 20 agents, so 2 groups of 10 agents, we will have 1 leader on each group. So 1 blue one and 1 green one. What is interesting in that example is that, as you can see here, so this is not t equals 0, but it's close enough. So you can guess that at t equals 0, it will quite have the same aspect. And you see that the total mass on the second group is bigger than the total mass on the first one. And so this is why the leader from the second group as its mass, which increase way quickly than the leader of the first group. And this is why this is the one who have a very, very high mass compared to the second leader. And it impacts the opinion, because you can see that the consensus is reached close to the opinion of the second leader and not close to the opinion of the first one. It's closer to the opinion of the second leader than the first one. So, well, basically, again, you see that here you will reach consensus. It's a flat, almost flat curve here. And again, the total weight will be concentrated on 10% of the population here, which is divided into different groups right here. Okay, so just illustration to show you, well, everything happened as we can guess it will, and it works quite well. Let me go to the second part of my talk here, which will be about the mean field approach. So the thing is, let's go back a few minutes to the classical Excelman-Krauss model. So you have here your discrete dynamics. And how do you usually prove those kind of results? Well, you notice the following thing. Well, when you are interested into the empirical measure, which is the quantity which is defined right here, you notice that your empirical measure happens to be a solution to your non-local transport equation, the one you are trying to reach at the mean field limits. And so once you have done that, actually the work is done, because you realize, no, not the work is done, you have to work a little bit, but this is the key idea, because then you use continuity with respect to initial data to conclude. And basically, so it's usually done in Wasserstein distance for this kind of problem. If you have mu zero probability measure, such that you have that limit at the initial data, you have for all t the convergence in Wasserstein distance of your empirical measure to your solution of this non-local transport equation. So this is how it is usually proven, those kind of questions. You are interested into the empirical measure. You notice that it is a solution you are to the equation you are aiming here, to the non-local transport equation, and you conclude with respect with the continuity with respect to your initial data. Let me point out here what I briefly said before, is that you have a significant loss of information here, because you started with knowing at each time where every agent was. And now you just know at what one point how many agents you have, but not which agents. You do not care, actually. You just know out that at that point, maybe I have 3 agents, maybe I have 1, maybe I have none, but I don't know if it's agent 1, 2, 3, etc. So you have a loss of information in that process, which was not the case in the previous framework. And so, of course, the question was, what happened in our case? So the idea was to be interested into a new empirical measure, which is this one. So we had the weight right here. And so in that case, as you can see, we have the same problem of loss of information. Now we know at one point what quantity of weight we have. We do not know from which agent it comes from. We do not know if it comes from several different agents. We just know which quantity of weight we have at what point. And so if you look at this, this empirical measure, you see that it's invariant by relabeling of the indices. So basically, if I switch indices between agents, it will not change anything. And it is, and this is the second point, which is new. It's invariant by grouping of the agents. So what do I call grouping of the agents? It's the case where you have several agents in the same point. So you have several agents in the same point. Let's here say that you have several agents in the point that I call xj. And so basically, how the mass is distributed among those at this point, you do not care. You just care about what is the total mass at this point. So you could switch masses, or you could distribute masses differently. It will still be the same. So let me be maybe more concrete with that example here. So here you have these two discrete systems with 5 agents. So the 3 last one are the same exactly. But as you can see, for the 2 first one, which are all in the point 0.5, you can see that for the first example, well, the mass are respectively 1.5 and 0.5, and respectively 1.25 and 0.75. And even if the weight is distributed differently into those two models, the empirical measure is the same. So this is what I call the grouping of agents. It does not see different grouping of agents. So this leads us to the notion of indistinguishability that we have defined for our model, which is the following. We will say that a system preserves indistinguishability if you start from two different models where all the particles are in the same position. I mean, particle 1 of the first model and particle 1 of the second one are in the same position. And when you are interested into cases where for the same model, you have several particles in the same point. So exactly the example I've shown you for the particle 1 and 2 in the previous example. This is that line here. And for those particles, the total sum for the two models is the same, even if distributed differently between the agents. Well, if you start from that at t equals 0, the evolution of your system will preserve it, and you still will have that at each time. This is what we call preserving indistinguishability. So, and actually, this is quite natural to ask for those kind of property for the models we want to look at, because we will be interested into the evolution of the empirical measure who do not see those things. So this is why we have to look at models which have these properties. But again, the problem is that if you ask that, where you reduce your span of models that now you can look at. And this is what brings me to this special class of weight dynamics that we have been looking at. So we have taken this particular form where S is a function which satisfies the 3 following properties. So it's bounded. We have this inequality, this regularity inequality right here. And we have this skew symmetry property, which is right here. And basically, we've taken this property just to be concrete. Actually, the only thing that matters here is that this property allows us to obtain the conservation of the mass, the total conservation of the mass. So you can replace this property by the fact that we are interested into functions such that we have conservation of the total mass. It still works. We've just taken this one particularly to be concrete. And so in that case, for this special class of weight dynamics, we have observed different things. We have observed that, well, as I say, preserve the total mass. We made sure of that. And it also preserves positivity. If you start from strictly non-negative measure, you stay strictly non-negative. And mainly, and that was my point, it actually preserves indistinguishability. And so far, this is the more general we have been able to be, to define those models who have this particular property. And so here is so this is a result that Nathalie obtained while we were working. She did in parallel work by the classical approach. So this used the same thing, the same trick that I explained you before. You start with your discrete system, you define your empirical measure. You see that your empirical measure actually is a solution to this transport equation with a source term. This is what is new. If you compare to the classical Excelman-Krauss dynamics, you have now a source term, and then you conclude with continuity with respect to initial data. So this is the classical approach. You have been able to obtain this result. As you can see, the source term, in the source term, the mass dynamics appear here this way. I'm not going to spend time on it because, as I said before, what interested us in our paper, it's not the fact that you have the mean field limit on itself. It's the link of the mean field limit with the graph limits we were interested in. And so the thing is, so as I said, if you start with a good initial condition, the solution of this non-local transport equation with source term happened to be the mean field limit to our system with this new special class of weights. Okay, and the question is, how can we connect that with the previous part about the graph limits? And so let me go back to the graph limit for a few moments. The thing is, for this special class of mass dynamics, the problem was that actually we could not apply our results directly, because here the form of this special class of weights did not fulfill the hypothesis we have taken in the first part. So we had to work a little bit in order to retrieve, to obtain again the existence of a solution to the graph limit with this new special dynamics, and with to obtain the convergence to the graph limit. It worked mainly thanks to the fact that these special class dynamics have some property such that the weight will be bounded, will be strictly non-negative. And because of that, we actually happen to be able to obtain a property for the psi, this particular psi, which is very close from the Lipschitz one on the previous case. But it works because M is bounded. So we have to work a little bit, but it still works. So in that case too, for that special class of weights, you also have existence of a unique solution to the graph limit, and you also have convergence to the graph limit in the same space of function. And here is the thing I wanted to say, the link. What we find interesting, it was on a remark on the paper of Zoazoa, which was pointing out that link. And so here is the thing. So you start from your graph limit now. So you already are at the graph limit level. You have a solution to your graph limit right here, associated to your special class of weight dynamics. And you define a measure here, which is this one, where M and X are the solution to this equation, which is right here. Well, actually, when you do that, it happens to be that this measure satisfies the transport equation with source term. So this is how you connect the two approach. And so this is why I was saying there is the graph limit is subordinated to the mean field limit is subordinated to the graph limit, which is not surprising that it's in that way, because we lose information in the mean field limit. So the other way would not have been possible, actually. And so, well, this is just easy computation to rewrite things in the good framework. And the connection, I think, is quite nice, actually. So that was the last result of our paper. And I will finish with some illustration about what I just said. So the model we will be interested in here is what we call the least influence gain influence. So so the idea behind this model, it's a world where you say that when someone is when you notice that someone is less influenced, it's more reluctant, for instance, to conspiracy theory. It's not that easy to convince. It makes him charismatic and he gains popularity. So that was the idea behind those toy model. And how you do it mathematically? Well, J to I is the influence of J on I. This is this quantity, which is right here. And EI is the total influence on I. So it's the sum of the EJ to I. So this is this quantity. And you will compare the influence on I to the weighted average of the influence in the population, which is this quantity right here. And so, as I said, if you notice that your the influence on I is smaller than the weighted average, so you are less influenced than the average, you will gain weight. And on the contrary, if you are more influenced than the average, you will lose weight and you will become less charismatic. So this is the toy model we invented. And so when you do simulation, actually, well, it describes what you think would happen. For instance, let's look at these two extreme points right here. When you are interested into the light green here, so you see that since it has the bottom at the lower edge, you see that it will not be influenced by. So sorry, what I didn't say is that in that case, of course, as you can see, since there are clusters, I've taken interaction functions which are compactly supported. And so since they are compactly supported, you can see that this one right here will not be influenced by many people because actually it is at the lower edge. So it will be influenced just by those one, and that's it. And so since he is not influenced by a lot of people, this is why you can see he's gaining weight this way. And this is why he's the one at the end who has the bigger weight. And what is interesting is the evolution of this one. As you can see, he starts at the upper edge. And so at the beginning, it's not influenced by a lot of people. So this is why he gained mass, he gained weight here. But then he joins these clusters here, and there are many people on it. And so he starts to be influenced by a lot of people. And this is why he starts to lose weight this way. So we were happy to see it was showing the things that you will think would happen. And so I don't know, do you see the movie? Okay, so you have the evolution of here the position and here the mass. Okay, so we already almost have reached steady state. You can see here, so this is a nice way of seeing in another way the clusters, because you see that you converge to a step function with 3 steps. Okay, so this one is not yet, has not yet converged, but it's not that far away. And you see the evolution of the mass. It did not change so much, but a little bit. And so again, this is an illustration of the convergence to the graph limit. The blue curve is associated to the graph limit, and the red one is xn and mn for our microscopic system with n equal to 50 only. So again, it worked quite well. And okay, so that's just screenshot in case of. And what is interesting in that case, what I think very nice is that we are in the case where we can compare the 3 different approaches. Now we can compare the graph limit and the mean field limit through this result I showed you before, because we have seen that what I called mu tilde, which is associated to X and M solution of the graph limit, is actually a solution to our macroscopic non-local transport equation with source term. So in red, it's the empirical measure associated to our microscopic system. In black, this is our measure mu tilde associated to the solution X and M of the graph limit. And in blue, it's the solution of the non-local transport equation with source term. And as you can see, again, it fits, it works quite well, and they add the same behavior as we can expect, which confirms the convergence. And this is nice to see a third different way to see the clusters, because you actually converge to 3 different directions. And so I guess I will stop with that, with just some open questions about what we have looked in this problem. Is that I have talked to you about those this special class weights, but this is the most general we have managed to be in order to satisfy our indistinguishability property. But is it the most general form we can take? Not so sure. And actually, if there is a more general form, will we still be able to perform the graph limit and the midfield limit for this form? And again, by our approach. What I didn't say, sorry, is that the mean field limit that we obtain by this approach, the result is actually weaker than the real one, because the real one is in Wasserstein distance. Here, it's a weak convergence. But again, that was not the result on itself that was interesting, but the link with the graph limit. So another question, which is an open one, is that, so I didn't talk about it right now in this presentation, but Medvedev also did a graph limit for W random graph associated to microscopic dynamics. We would like to do an equivalent of this for our type of model and to see if it still works. And finally, but this is questions which are more related to the first type of question Anastasia looked at, is that, do you always converge to steady state, similar to the one we usually know, or maybe some different things happen? Okay, and I think I will stop on that. Thank you for your attention.
Thank you for this very interesting talk. Thank you.